Now we will move on to a very separate and a very different concept, which is dot product. And dot product is nothing but one multiply operation and one sum operation. So let's go back to matrix algebra. Isn't it interesting that all these things are interlinked? Geometry is linked with trigonometry, trigonometry is linked with exponentials, and now exponentials are linked with matrix algebra. So let's start a quick review of dot product. I have defined here a vector 1, which is having elements 1, 2, 3. So consider it as a row of a matrix. And I have defined another vector 2, which is 3, 4, 5. Consider it as a column of the second matrix. And we know that in matrix multiplication, a row multiplied by column is what the answer is of the matrix multiplication. So essentially 1 will get multiplied by 3, 2 with 4, 3 with 5, and all of them will get added together. So 1 multiplied by 3 is 3, 4 multiplied by 2 is 8, that is 11, and 5 multiplied by 3 is 15. And when we add them all together, this should be 26. So one way of doing this is that we just take these two vectors and use this function multiply, and then operate a sum operator on top of it. That's going to be exactly the same as this function, which is dot product, and the results are going to be the same. So here we are. So, but what has it got to do with sinusoids and exponential? These are just plain numbers. These are just vectors. So instead of using these vectors, let's use sinusoids and see how they behave when the dot product is undertaken. So let's take the dot product of sinusoids. In this case, again, I'm going to generate two signals, sampling at 1000 hertz, and the time duration of these signals is 2 seconds. So first signal is having parameter amplitude as 1, frequency as 5 hertz, and a 0 phase. And I'm going to generate a sine signal out of it. And the second signal is again, amplitude 1, frequency 5 hertz, and a 0 phase. So both the signals are basically identical. And here is the second signal. Again, I'm putting all these values inside a sine function and generating that signal. So both of them, signal 1 and signal 2, are sinusoid, having exactly the same frequency, phase, and other parameter amplitude. And I'm going to calculate the dot product by using the above two methods, which is using sum and multiply, as well as using the built-in function called dot product. So here we are. Then I'm computing the dot product between signal 1 and signal 2 by method 1, and then by method 2, and I'm rounding off the results to decimal places. And let's see what happens. I'm going to just print out the dot products and see how these signals look. So here we are. Firstly, we see that dot product is a very large positive number by both the methods, by multiply and sum method, and by directly using the dot product function in Python. And the second is that we see that since both the signals have the same frequency, phase, amplitude, etc., they are just overlapping. So one signal is solid blue line, which is the original signal 1, and the dashed red line is signal 2, and they are overlapping with each other. Now let's see what happens if we try to change the frequency of signal 2 by some amount. So here we are. This is the other parameters for signal 2, and let's say instead of 5 hertz, let's make it 6 hertz, and see what happens to the dot product. So clearly here we see that the signal 2, which is the red part, is having more frequency. So 1, 2, 3, 4, 5, 6. So within 1 second time interval, there are 6 cycles of this. So 6 hertz is confirmed. And the blue signal, which is signal 1, is having 5 cycles, 1, 2, 3, 4, and 5 in the 1 second interval. So it's at 5 hertz. But the most surprising part is that the dot product has become 0. From 1000, it has become 0. Why has that happened? Let's try any other frequency. Let's say any arbitrary frequency for signal 2. Let's say 10 hertz. 10, which is a perfect harmonic of 5. And again, we get 0. This is really surprising. Let's pick up any arbitrary frequency. Let's say 17 hertz. And again, the dot product is 0. So what is happening here? Let's experiment further. So instead of now keeping it at 17 hertz, let's go back to the original frequency as equal to the signal 1 frequency, which is 5 hertz. And let's see whether this is, so dot product has increased back to 1000. What happens if we try to change the phase? Does it change the dot product? So let's generate a phase difference of pi by 2. But the frequency is the same. There's no difference. Frequency is 5 hertz, amplitude is 1, frequency is 5 hertz, amplitude is 1. Only here it is 0 phase, and here it is pi by 2. And let's see what happens. So we can clearly see that the sine has become cos and cos has become sine because of phase shift, and the dot product has again gone to 0 from 1000. Now this is a very interesting thing here. Unless the phase and frequency of the two signals match, the dot product between them becomes a very low value, and at times it becomes negative value too. So how can we use this? How can we use this fact in our application? Or is it just happening by coincidence? Let's continue with this experiment and see what can be done. So instead of now keeping this second signal as fixed frequency at 5, I'm going to generate a second signal which is a chirp kind of a signal which is generating multiple frequencies. And let's see what happens to the dot product. So I'm going to disable this signal 2. The signal 1 remains the same at amplitude 1 and 5 hertz. And I'm going to disable signal 2 completely. And I am going to now generate a second signal whose frequency is varying from 0 hertz to 10 hertz in a step of 0.1 hertz. And I'm going to then calculate the dot products between this signal and the signal 1 and see what's happening there. And I'm going to sweep these frequencies from 0 to 10 hertz in this particular loop and generate these harmonics, and then create, calculate the dot products between the harmonic signal and the original signal 1 and plot them as a stem plot. So here we are. So I have a signal, a pure sinusoid at 5 hertz. This is my original signal. And then something very strange is happening. I'm sweeping, so this axis is the time axis, and this is the amplitude axis for signal 1. And the second plot is the Fourier transform plot or the harmonics plot, where this x-axis is in hertz, it's a frequency axis, and the magnitude of the dot products is on the y-axis. And we see that when we are sweeping through these frequencies, starting from 0 hertz to 10 hertz, only when this frequency is matching with the original signal's frequency, the dot products, they rise up in magnitude. Otherwise, they all become 0. Is it by coincidence? Let's try to manipulate this signal and see the effect. So we are going to now change this frequency for signal 1 from 5 to say 2 hertz. And rest everything remains the same because we are sweeping through 0 hertz to 10 hertz as far as signal 2 is concerned. So let's see what happens to the dot products. So as you can see, there are only 2 cycles in 1 second windows where the signal has become 2 hertz. And surprisingly, at 2 hertz, this is the only point where we are able to detect the energy, where the dot products are having significant magnitude. That is 0.5. Recall we have an amplitude of 1, and in this signal we have been able to recover a magnitude of 0.5. The reason why 0.5 is that we are just considering one part of the complex signal, that is sine wave. If we use a complex wave, that is the other part, the complex part 2, then we'll be able to recover the complete amplitude of 1. So as you can see that the harmonic is only generating sine wave currently, it is not generating cos wave. So only half the amplitude of the spectrum has been recovered here. But more important part is that unless the frequency of the second signal matches with the first one, there is no output from the system. And this principle is called as orthogonality. There are various terms for this. When we were children, we were taught a very simple term for perpendicularity or 90-degree apart. And then as we grew up, there were various terms coined for that. Sometimes normality, sometimes it is imaginary axis, sometimes it's 90-degree phase shift. Orthogonality, essentially it means just the same thing. It is a 90-degree phase shift. So this is a very important concept, that when we take dot products of 2 signals, until and unless the frequencies and phases are matching, the output of the dot product is 0. That means signals are orthogonal to each other. And this fact can be utilized as in frequency detection application. And this is exactly what DTFT is all about. It is trying to detect the frequency of the original signal.